Okay, hi. So today's just kidding. You all can't see it. Okay, now you can. So today is the TLS lecture. Really cool lecture. But before I talk about that, I'll give you one quick project 2 tip. So I guess today we'll talk about append efficiency unless someone else is intensely curious about something else. So this one, hopefully we all agree by now that append efficiency is not measured in terms of the amount of compute that you do. It's not measured in terms of space efficiency. It is specifically measured in terms of bandwidth efficiency. And the way that bandwidth efficiency is measured is every time you want to read something from data store, you have to call data store get. And that downloading of data counts against you in terms of bandwidth. Anytime you want to change something on data store, you have to download the data, change it, and re-upload it using data store set. That also counts against you when it comes to bandwidth. So the total amount of bandwidth that you use when you append to a file has to be constant size, no matter what the user's settings are. So whether or not the user has one file or a million files, the total bandwidth of append has to be constant. Whether or not the user has appended to the file once or a million times, the total append bandwidth has to be constant. Hopefully, this is all stuff that we already agree on. And so I guess any questions, or do we all agree that bandwidth is the way that you measure append efficiency? Okay. So question? Yeah.
It's okay for it to scale in the size of the append, right?
Yeah. So the question was, is it okay to scale with the size of the append? That's okay. That's the only thing that it's okay to scale with. Yeah, great question. Okay. So now that we all agree what bandwidth is, and hopefully is in your design, if not, this would be a good time to update your design so that it satisfies the bandwidth requirement. The way that you would test something like this, because we didn't provide any bandwidth tests, so it is on you to write these tests. And all the tests that we have on the AutoGrader are tests that you can replicate yourself. So what I would recommend doing is if you want to check, for example, that the bandwidth doesn't scale with file size, then what I would do is I would come up with several different scenarios, maybe like 5 different scenarios. And in the 5 scenarios, we have all else equal. So the same user, the user has the same number of files. The name of the file is the same. So we come up with 5 different scenarios where everything else is the same. And the only thing that we vary in the 5 scenarios is the size of the file. So maybe in scenario number 1, the user with the same username, the same file name, same everything, creates a file that's 10 bytes. And then in scenario 2, same username, same file name, everything, 100 bytes. Scenario number 3, same username, same file name, 200 bytes. And you can do this for several different scenarios, and then check the total amount of bandwidth for every single scenario. And the way that you would check the bandwidth for each scenario is you would check, there's a helper function that we provide, or I think we provide, that gives you the total amount of bandwidth that you have used so far in this test. So you can check, before I call the append, what is the total count of bandwidth that's been used? After I call append, what is the total count of bandwidth that have been used? And if I compare those 2 numbers, the difference in the bandwidth before and after the append tells me the amount of bandwidth that that particular append used. So there's a helper function that does that for you. You call it before and after, you check a difference. That's my recommended way of doing it. There are certainly other ways, but that's what I like. And then after that, what you can do is you can check in these 5 scenarios where the size of the file was different, what was the bandwidth for each of these 5 things? And if they were all constant or very close to constant, then you know you've got a solid append when it comes to scaling with the file size. However, if you see a linear pattern where as the file size gets bigger, the bandwidth number also starts to increase, then maybe you have a problem that you want to start sniffing out. So that could be one way to deal with file size. You can do the same thing for any of these other ones. You could say, I have different scenarios where the user has 1 file, 10 files, 100 files, 1 million files, and check what the bandwidth is across these 4 different scenarios, see if they scale. So those are my tips for how you might test for bandwidth. You can use the helper function that we provide to check how much bandwidth is being used. And then you can make up scenarios to see if your append scales with any of these things. That's my tip for getting a perfect append, but it's certainly up to you. Okay. Questions, thoughts? Is everyone good with append? People always mess this up and think that it's time efficiency or space efficiency. It is bandwidth efficiency. That's what makes append tricky. Yeah, question? What is the corresponding helper function? I don't remember the name of it off the top of my head, but it should be somewhere in the spec. So if you dig around, I have faith you'll find it. Okay, maybe somewhere in here. Bandwidth? something like that. Yeah, here it is, measure bandwidth. Okay, so there's an example. Okay, cool. So that's it for project 2. Hopefully it's going well. We are nearing the end of it. So, we wish you good luck as you enter the home stretch. Okay, let's talk about TLS. So last time we left off, I was at layer 4, and at layer 4, there were 2 choices of protocols that you can use. Both of them build on IP. So in both cases, you're relying on IP's power to send messages anywhere in the world. And on top of that, you're possibly building something that adds other features. So both TCP and UDP added the idea of ports, which means that if one computer would like to talk to another server, but there are 2 different connections going on, like there's different applications talking to each other, the ports can help you identify which connections are which. And TCP in particular additionally adds reliability. So it takes the IP protocol, makes it reliable. And the high level ideas were that we added some sort of ordering on the bytes. We stamped every byte with a number. And we also added reliability by forcing each side to acknowledge every message that it receives. So if you receive a message, you must acknowledge that you received it. And if you do not acknowledge, the message will get resent until a message gets sent and it gets successfully acknowledged. We talked about the ways that this is implemented. There are some flags that we need to implement all of this stuff. We have to add sequence numbers. We talked about those. And the 2 classes of attacks, they basically said TCP, there was no cryptography. There will be today, but there was no cryptography last time. So if an on-path attacker or a man in the middle would like to read your communication, they can. If they would like to tamper with your communication, either by injecting data or injecting a reset packet to stop the connection entirely, or by starting a brand new connection, they can. And the off-path attacker is the only one that we can kind of protect against. And the way that we do that is by randomizing the sequence numbers or the starting sequence numbers so that the off-path attacker has a hard time guessing what the sequence number is because they can't read it. Okay, that was the summary. It was all stuff from last time. So today we are finally going to add one more layer on top of TCP that finally introduces all of the cryptography that's going to make these network connections secure. So like along the networking journey, remember there've been like 3 different attacks where I just kind of shrugged and said, it's okay, we'll deal with it when we talk about some higher layer. Today is that day where we defeat all of those attackers that we've like left in the dust so far. Okay. So to do that, we're going to have to build another layer. And this is another example of how this model is 1970s outdated. So back in the 1970s, no one really thought about secure communications over the internet. And so we had to add that in. It is not really layer 7 because you can build stuff on top of TLS, like the web is built on top of TLS. It's not layer 4 because we already built layer 4. So I am going to call it layer 4.5. I don't know if that's like what people actually call it. Again, we're shoving this into an outdated model. So I know that this is probably not how you've learned how to count in your other classes, but we are counting 1, 2, 3, 4, 4.57. Okay. And the reason why we don't use 5 and 6, they're outdated. They represent other things that we don't use anymore. Okay. All of that is to say, we have TCP built for us. We did it last time. We now have the ability to use the byte stream abstraction. We get to think in terms of connections. So for all of today, you're never going to have to stop and stress out about, oh, but what if the packet is too large? How do I split it up? Or what if the packet doesn't show up? Well, I have to resend it. For all of today, we don't have to stress about that because we are going to be sending all of our messages over TCP. And TCP is already guaranteeing to us the byte stream abstraction. I can feed in any bytes that I want. They're going to show up on the other side. No problem. So we do not have to worry about any of that stuff today because we're building on top of TCP. And the goal is to still provide a byte stream abstraction. So I'm not going to change the fact that the end user is going to think in terms of connections. I'm not going to change that. However, I'm going to build a layer of cryptography on top of TCP so that the connections that go back and forth are more secure against those on-path and man-in-the-middle attackers. Okay, that's the goal. We have TCP as the building block. It's done for us. We don't have to worry about rearranging packets and putting them in order. And we're going to build a cryptographic system on top of it that gives us the ability to send messages securely. Let's do it. Okay. So just like every design task so far, I'm going to first tell you what the goals are, and then we're going to start piecing together something that hopefully achieves those goals. So here are the goals. Some of them seem maybe more obvious, some seem less obvious. So The first one that would be nice is confidentiality. We've seen this one. We don't want people over the network to be able to read the messages that we sent back and forth. In TCP so far, they can do that because TCP has no notion of encryption. But after we introduce confidentiality, now the attackers have no clue what I'm saying when I send messages back and forth. We would also like integrity, so we don't want attackers to be able to change what I am saying without being detected. If the attacker tries to change something, I want to be able to detect it. And kind of a corollary of integrity, or like something related to integrity that we've sort of hinted at for all of class, but I'm going to make it very explicit this time because it's a common attack, is the replay attack. So the replay attack, I guess the way that I think of it is, if all the messages are totally secure, they have confidentiality, they have integrity, then maybe an attacker sees the packet going across the channel and has no idea what it says. There's confidentiality on it. The packet is unreadable to the attacker. They don't know what it says. Also, the packet has integrity, so the attacker can't mess with it. But what if the attacker wrote down the exact sequence of ones and zeros in that packet? So they wrote down the exact packet. They have no idea what it means or what the MAC says or how to change it, but they wrote it down. And then they sent that exact same sequence of ones and zeros to the recipient a second time. Would the recipient think that the original sender meant to send the message twice? And if so, that constitutes a replay attack. I am replaying the message, even though I have no idea what the message said, and I have no ability to change the message. And if your scheme is not secure enough, you might be vulnerable to replay attacks, because the MAC could still be valid if you haven't changed it at all. You're just copying the ones and zeros. The original message could still be valid if it's just a bunch of ones and zeros, even if you don't know what it says. And you could possibly trick the recipient into thinking that it was sent 10 different times. Maybe, depending on the way that you set up this protocol. But we don't like that, because imagine if the message just so happened to say pay $10 to Mallory. Well, now if I send this message and I replay it 10 different times, then Mallory is going to make a lot more money than she should, and we don't like that. So we would like to also stop replay attacks at the same time as providing integrity. So it's kind of a side effect or another property that we would like, but something we haven't made explicit until today. Now it's very explicit. Okay. And the final thing we would like is authenticity. And so here, the property we want is that we would like to make sure we're talking to the legitimate server. So when my computer makes a connection to google.com to get these slides, I would like to make sure that I'm talking to the real google.com and not somebody who's pretending to be google.com. That is something that I would like to ensure. Okay. So those are the properties that I want. Confidentiality and integrity, we've seen those before. Replay attacks are kind of new. And here I'm defining authenticity very specifically to say, I want to make sure that the server that I'm talking to, that I know exactly who they are, and that I can trust that this is the real Google, and it's not someone who's just pretending to be Google and sending me a bunch of garbage data. Okay, so to do this, we're going to build a handshake. We've already built handshakes before, but this one is the TLS handshake. So it's kind of long, so bear with me. We're going to go through the entire handshake, and then I will break it down and talk about how each part achieves the goals. So we'll go through the handshake first. Some of the steps might seem kind of like incomprehensible at first, and that's okay. It's a long handshake. But I guess without further ado, we'll jump into it. So the first thing to remember is that this handshake is going on over TCP. So you never have to stop and say, oh, what if the message is too long? Or what if the message shows up out of order? Don't care. TCP is taking care of it all for us. So everything that we send back and forth is being sent over TCP. I do not have to worry about reliability. Okay, so get that out of the way. There is a TCP connection. It had to be formed first. So first, the two sides are going to say hello to each other. So here they are saying hello. The main thing that is important in these two hello messages, there's a lot of stuff. There are details that we're going to abstract away for now. But the most important thing that they send in this exchange is a sequence of random numbers, or two random numbers. So the client picks their own random number. I'm going to call it R sub B, sends it to the server in the client hello message. Server picks their own random number, R sub S, sends it over in the server hello message. So now there are two random numbers that have been exchanged. I haven't used them yet, but that is what's happened in this step. Okay. And so intuitively, if you want to start building intuition on how this works, you can think, well, the random numbers are going to make sure that if I do this handshake 10 different times, there's going to be at least one thing different in every one of those handshakes, because these are random numbers and they're going to change every time. So intuitively, that's why they're needed. We'll go into a lot more detail about why each step is necessary, but for now, they've exchanged random numbers. Technically, this is a bit of fine print. They're also going to agree on some cryptographic algorithms at this point. So for example, they could choose to use HMAC, they could choose to use AES-based MAC, like the one you saw on the midterm or something. So there's a lot of different algorithms that they could choose to use. They could choose to use AES-CBC or AES-CTR. Which one will they choose? They're going to agree upon that stuff here as well, but that's more fine print. The random numbers are what's really important for the security of this step. Okay. At this point, it's now time to figure out who the server is. Remember, one of our key goals is to make sure we know who the server is. So the first step that we're going to do on our journey to making sure we know who the server is we're going to ask the server to send a certificate, and the server is going to send over its certificate. So at this point, you need to go back into the dusty cobwebs and think about what is a certificate. Remember, it's kind of a weird name. I would have called it something different, but I didn't invent it, so we're calling them certificates. But remember, a certificate is nothing more than the server's public key signed by someone else that you trust. That's it. So the certificate contains the server's public key is this, and that message gets signed by the private key of someone else that you trust. You can use the trustworthy person's public key to verify that that's true. And here the trustworthy person is the certificate authority. How do you trust them? More on that later. But the key here is that you get a certificate. It's a fancy way of saying it's just someone's public key signed by someone else that you trust. You can validate the certificate by checking that the signature is correct. And if you check the signature and it checks out, what do you know at this point? So another thing that's really helpful when you go through a complicated handshake like this is try and think about what are the things that you know at any given point. So at this point, do you know that you're talking to the server? Well, not really, because anybody could have sent a random number. Anybody could have sent a certificate. Those things are public, right? I could send the public key of someone else. That's okay. So at this point, the only thing that you know for sure is you know the public key of the server. Why do you know that? Because the certificate told you this is the server's public key. It's signed by someone you trust. So you have 100% confidence that this value is the server's public key. Do you know that this person is the actual server with that public key? Who knows? Someone else could have sent you the certificate. However, you are at least confident about what the server's public key is. That's what this step is for. So it's easy to overthink this step and think, oh, the certificate tells me that I know who the server is. It does not. It just tells me what the server's public key is. But I'm not all the way there yet. Okay. Certificate is sent. I know what the server's public key is. And now we keep going. So at this point, we're going to do a pre-master secret exchange. And this one's kind of tricky because there are two purposes of what we're about to do. There's also two different ways to do it. So things are about to get a little complicated. So there are two things that we want to do. One thing we want to do is we still want to know we're talking to the real server. And so somehow we need to know that this is the person corresponding to that public key. I know what the server's public key is. I want to make sure that this is the person who owns the corresponding private key. So remember, in public key cryptography, the private key is kept to yourself. The public key is published to the world. You know the public key that's been published to the world. You trust it from the certificate, but you have to know that this server is the person with the corresponding private key. That's how you know this is the server. So somehow we're going to have to issue a challenge that lets us know whether or not the server owns the private key. And if the server can solve the challenge, we know they own the private key. If the server is unable to solve this challenge, then we know they're probably an impersonator. So that's one thing we're going to try and do in this step. And at the same time, because we can, we're also going to try and get a shared secret between these two people. So far, no shared secret. Random value certificate, they're all public. So we would like to get a shared secret. And maybe it's not totally obvious yet why this is useful, but you can imagine when I'm going on my way to do cryptography and encrypt things and MAC things, it would be nice if they shared a secret. So I'm going to try and do that first and then use the secret in interesting ways later. Okay, those are our two goals. Now we have to figure out two different ways to do it. So one way to do it is to take advantage of RSA. And this is what that version looks like. It's a single message. There it is. And so there's two different ways to think about this, depending on which purpose you're trying to solve, or which goal you're trying to solve. So first, I'll tell you what it is. All that you're sending as the client, you're sending some random secret. So the client picks the secret. They can just choose it randomly. They encrypt it with the public key of the server, send it to the server, that's it. So it's just the pre-master secret, which is some random value chosen by the client, encrypted by the public key of the server. Okay. We can think about this two different ways. So one way to think about it is, why does this guarantee that we are talking to the real server and not an impersonator? And the way I think of it is, the client is issuing to the server a challenge. The client is saying, okay, server, you claim to be the person who owns the private key of server. Okay, well, I'm going to make sure that you're not lying. And the way that I'm going to do that is I'm going to send you this message encrypted with your public key, or what you claim is your public key. And if you are who you say you are, in that you own the private key, then you should be able to solve my challenge, decrypt this, and get the secret, so that we both agree on the secret. However, if you are not who you say you are, you're an imposter, you're an attacker, then when I send this message over, then the fake impersonator of the server is not going to know the private key of the server, and we'll have no hope of decrypting this, because you have to have the private key of the server to decrypt this message. So one way of thinking of it is that this is a challenge issued to the server, and if the server is able to solve the challenge, then we know it's them. If the server is not able to solve the challenge, then we know it's some impersonator. And the other thing that this does at the same time, because there are two different goals that we're trying to check off, is that this is also going to help us establish a shared secret. So if the server is who they say they are, then they can decrypt this message, and now the client and the server both know the secret. Why does the client know the secret? Because they chose it. Why does the server know the secret? Because they got sent an encrypted version of it. They decrypted it. And nobody else should be able to know it, because I didn't send this secret in plain text. I sent it encrypted. Okay, that's the RSA approach. It checks off both of my goals. Now I have a challenge that only the server can solve, and I also have a shared secret that both of them have. Okay, questions? Yeah.
What if the server like is fake, but it talks to the real server?
What if the server is fake and talks to the real server?
Yeah, and a challenge to the real server.
Gotcha. So you could, this is probably like a little bit beyond the scope of just seeing it for the first time, but the question was, what if the server is like relaying messages forward? Well, the impersonator is not going to get the plain text of the pre-master secret at any time. So, right? And you'll see this when we finish the handshake, but the server is not going to get the pre-master secret in any form except this encrypted form. So the impersonator still won't know what the secret is. Okay, but I'll try and finish the handshake and we can ask more later if you're curious. Okay, so this is one possible way to achieve those two goals, but there's actually a second way to do it. And so here, I'm not actually introducing another step. I am offering to replace this step with a completely different alternative. So I'm going to throw out the pre-master secret idea with the RSA, and I'm going to put in something different. And I'm going to put in something based on Diffie-Hellman. This is an equivalent approach, right? Both of these achieve the same goals, and we'll talk about which one is better later, but they achieve the same goals. And so in this approach, I'm going to leverage the power of Diffie-Hellman. So I go back and I remember, okay, Diffie-Hellman is this way where two people can share a secret, even without exchanging, or even so that attackers looking over the channel don't know what the secret is. So the way that we're going to do that is just classic Diffie-Hellman. Server sends G to the A mod P, client sends G to the B mod P. They both derive G to the A B mod P, and now they both agree on a shared secret, like typical Diffie-Hellman stuff. And so that solves our first challenge, which is how do you make sure that there is a shared secret that they both know? You use Diffie-Hellman. But one problem is that, remember, there were two goals of this step. One of the goals was to make sure that they both share a secret. Check, Diffie-Hellman does that. Second goal, however, is we need to make sure that the client is who they say, or sorry, the server is who they say they are, right? No fake servers around here. So how do we make sure that's true with Diffie-Hellman? If you just send plain Diffie-Hellman, there is no proof of who the server is. If we just do plain Diffie-Hellman, anybody can send that G to the A mod P, right? G to the A mod P is some random value. Anybody is licensed to send this, including any attacker. So Diffie-Hellman by itself does not tell me that the server is who they say they are. So I need to add in that extra challenge to tell me if the server is who they really claim to be, or if they are an imposter. So the way that I'm going to do that is I'm going to additionally ask the server to add a signature on its Diffie-Hellman handshake. So the server is going to send G to the A, but it is also going to sign G to the A with its private key. And then I can use the public key to verify that the signature checks out. Why does this guarantee that the server is who they say they are? Because if the server was fake, they would not be able to generate the signature. And when I try to verify it, I'll be like, oh, wait, signature didn't check out. You are not the real server. So by signing this half of the Diffie-Hellman handshake, I'm guaranteeing that the server is who they claim to be and not an imposter. Okay. So that's what checks off the two goals. The regular Diffie-Hellman checks off the goal of getting a secret that they both share, and the additional signature allows me to make sure that the server is who they really are and not someone pretending to be the server, because only the real server could have generated the signature. Someone pretending to be the server would have had no hope of generating the signature. Okay. Great. So these two steps, again, they are alternatives, right? You could have chosen either one, and later we'll see which one is better. But for now, either one is okay. So at this point, what do we know? At this point, we know who the server is, thanks to this challenge. I'm pretty convinced that this is the real server or an imposter, right? And so now we also both have a shared secret. So now it's time to start deriving a bunch of keys. And so this is the point where we realize, like, okay, I remember from the cryptography unit that like key exchange or key reuse is kind of bad. I don't just want to use the same key to encrypt everything and MAC everything. So I'm going to take this one pre-master secret, the one secret that we both share, and we are both going to independently derive a bunch of new keys, right? And so here we're just going to be paranoid and just go crazy and like derive a bunch of keys. In particular, we're going to derive 4 of them. And you can think of it as this is going to allow me to split the key for encryption and the key for macking. This allows me to avoid key reuse where I use the same key in 2 different algorithms. So both sides are going to derive 4 different keys. Both sides are going to know all 4 keys. And all of this happens offline. So they are not sending keys to each other. They both know the starting secret. They can both run the same deterministic algorithm, some PRNG, some hash or something like that. And they can both get 4 different keys that they both know. Why 4 and not 2? Also something for later. I told you TLS has a lot of moving parts, but for now, the important thing is that they both compute keys and they do not have to share the keys over the channel. They both know the secret, so they can both derive the keys. Okay. So what do we have at this point? At this point, both sides have a set of keys that they can use to communicate that no one else knows, and the client and the server know who the client knows who the server is. So at this point, it is now time to make sure that the handshake has not been tampered with, because all this time, when I've sent all this stuff over the network, a lot of it was like unsecured. For example, G to the B mod P, if I choose to use this option, someone could have tampered with that. Or what about those random numbers at the very beginning? Someone could have tampered with those too. So somehow I have to make sure that the messages were not tampered with. And the way that I'm going to do that is I'm going to exchange MACs. Here, when I use MACs, I'm referring to cryptographic MACs, not MAC addresses. That's something that happens at the layer 2 or whatever. Today's all about cryptography. This is the cryptographic MAC. So intuitively, what I'm doing is I think back to MACs, and I remember, okay, MACs are a way to help me check that messages have not been tampered with. So if you're convinced by that, you can abstract away the exact way that this is being done and just remind yourself that the MAC helps me check if any of the things sent so far have been tampered with so far. Okay, if you want to be really pedantic, you can think about what specific key they would use and how they would regenerate the MACs to make sure that they check out correctly. But for the purposes of just seeing the handshake for the first time, I think it's good enough to just say the MACs are a way to make sure that nothing has been tampered with so far. And we can do it because both sides have secret keys that they share. Okay. And finally, after all of this handshaking stuff, we finally have a series of keys that they both share. We know who the server is. And finally, we are able to send messages back and forth. They both share secrets that they can use to encrypt things and MAC things. The client is confident who the server is. It's time to start sending messages. So now we can use encryption and macking, hopefully in some secure way. Older versions of TLS use bad ways of doing it, but somehow we're going to combine encryption and MACs to send messages back and forth. Now the messages have integrity and they have confidentiality, and we are done. Okay, that's your first taste of the handshake. We're going to start digging really deeply into it. So if you have questions, maybe hold them for a couple slides. Okay, so at this point, you've seen the whole handshake. They exchange random numbers. The server sends a certificate, which tells me what the server's public key is and nothing more. At this point, there's a pre-master secret exchange, and the pre-master secret exchange could be RSA or it could be Diffie-Hellman. But in both cases, they're going to allow me to get a shared secret and also convince me that the server owns the public key. And then at this point, they're going to send Max to make sure that nothing has been tampered with so far. And if they both agree nothing has been tampered with, it's time to start encrypting and macking all my messages. Okay, that's the whole handshake. It barely fits on the slide, so this is kind of condensed. But now we can start thinking about all those 3 goals that we had from before and think about, did we actually get all of those checked off? So the first one I'm going to do is, did we successfully make sure we're talking to the legitimate server? Remember, one of our goals was, I don't want this to be an imposter pretending to be the real server. I want to make sure this is the real server. So how do I make sure that's true? Why does this handshake guarantee it? Well, it guarantees it through 2 different steps. So one useful thing when you're seeing this handshake for the first time is think, there are like so many different steps. Which of the steps guarantees each of the properties that I care about? So here, the property I care about is, am I talking to the real server? The way that I check that is, there's 2 things that are needed. The first thing is the certificate. I need the certificate to know what the server's public key is. Otherwise, I don't know. The certificate is a way to know what the server's public key is and be 100% confident because the public key is signed by someone else who I trust. And furthermore, knowing the public key by itself does not guarantee to me that this is the server. That's the part that's kind of tricky. If I know what your public key is, I don't know who you are because the public key is public. Anyone could have known it. So the second step that is absolutely necessary to make sure that I know who the server is that exchange, either using RSA or Diffie-Hellman, because that is a challenge that only the server with the private key can solve. So I need to know what the server's public key is. The certificate provides that. I also need to know that this is the person with the private key. And I don't need to know what the private key is, but I need you to prove to me that you know the private key. And the 2 ways to do that are either issue a challenge. If you know the private key, right? Oh, you think you're so hot, you know the private key. If you do, then you need to be able to decrypt this pre-master secret that I generated and encrypt it with your public key. Or in the Diffie-Hellman option, oh, you think you know the private key? Prove it to me by signing your half of the Diffie-Hellman exchange. In both cases, if the attacker is an impersonator who doesn't know the private key, then they would not be able to complete this challenge. And so they would fail at that step. And when they fail at that step, something later down the line is going to catch that. So maybe the MAC exchange will be messed up or something. You can think about that kind of on your own time. But the important thing is that only the legitimate server could successfully clear these steps. Okay. That's one of the goals checked off. Let's think about a second goal. So the second goal is, did we successfully provide confidentiality and integrity over the messages? It seems kind of convincing. Like, I exchanged some secrets and no one else knows the secrets. Can I be very confident that no one else knows the secrets? Well, the way that I can convince myself is, the attacker doesn't know the pre-master secret. That was the original secret key from which all future secrecy is derived. And the attacker doesn't know the original secret. Why is that? There's 2 different arguments I have to make. For the RSA case, I think, okay, well, how was that pre-master secret sent? It was sent encrypted with the server's public key. If you don't know the server's private key, you have no idea what that secret says. So we're good. In the Diffie-Hellman case, we appeal to the properties of Diffie-Hellman, and we remember, if you see G to the A mod P and G to the B mod P, you have no hope of knowing what G to the AB mod P is. So we're good there as well. So in both cases, we're appealing to the cryptographic protocols to guarantee that the attacker doesn't know the original secret. If the attacker doesn't know the original secret, and all the other secrets were derived offline from the original secret, then the attacker has no way of knowing those derived secrets either. It was done offline, so the attacker has no extra hints to use to figure out what those derived secrets are. And so if the attacker doesn't know the original and the derived secrets were done offline, the attacker should also not know what the derived secrets are. This is not a formal proof, but hopefully talking through it seems reasonable that the attacker doesn't know what those derived keys are. And then we're using those derived keys to encrypt and MAC things. So hopefully it feels okay that the attacker is unable to figure out how to decrypt those messages or how to tamper with them because of the MACs. Okay, so seems reasonable that the messages are secured, but there is one extra thing. Remember, we said integrity is great, but there's a replay attack problem that we have to solve. So let's solve that now. So there are actually 2 types of replay attacks. Like, this is all TLS, by the way. I'm always like, okay, there's this one property, but it's actually 2 properties. It happens all the time. TLS just has a lot of complexity like that, but it is kind of interesting. Anyway, TLS replay attacks, how do we stop them? Turns out there are 2 replay attacks that I care about. So one of the replay attacks is, what if I wrote down a message, a bunch of ones and zeros, I have no idea what it means or what it decrypts to. What if I wrote it down from a previous TLS connection, and then now there's a completely separate connection going on, and I want to take the messages from the past connection and inject them into the current connection? How do I stop someone from doing that across different connections? Well, for this one, the step that I'm going to appeal to argue that this is okay is these first two steps. Because these first two steps where I exchange the random numbers are going to make the symmetric keys different every single time, right? So I guess one thing that I should have made really clear that I didn't, so that's on me, is that the derived keys also throw in the randomness. So I guess I forgot to mention, the randomness does get used. We don't just generate random and throw it away. The randomness gets used at the point at which I derive the symmetric keys. So I wonder if the slides are just wrong. I would hope not, because that would be kind of an L on my part. Okay, did we say it? Yeah, we did. Okay, I just forgot to say it out loud. So there it is. The symmetric keys are not just derived from the original secret, but we also throw in the randomness. And the reason why that's so important, the randomness that I throw in, the reason why that is so important is because of these replay attacks across connections. Because I am throwing in the randomness to generate the derived keys, if I have two different connections, the random numbers that get thrown in to generate the derived keys are different. And so the ultimate keys that I end up using in these two connections are different. So if I take a message from one connection, copy down all the ones and zeros, and try to shove that message into a different connection, it will fail because the symmetric keys are different for every connection. So those random numbers, they come in handy for this type of replay attack. Okay. But there's another type of replay attack, which is, what if someone copies down the ones and zeros from the current connection and then tries to inject them again in the same connection? They're not trying to inject it into a different connection, but the same connection. How do we stop that? This one turns out I have to add another feature to TLS that I haven't done so far. So here, one way to think of it, I think the cleanest way to think of it the first time you see this is think about timestamping all of your messages. So instead of just sending a message like, pay Mallory $10, make it say something like, pay Mallory $10 sent on November 1st, 5:47 p.m. Okay, great. And if I write down the exact timestamp, I can even be more precise. Then if someone tries to copy the message and send it again, the timestamp's not going to check out. And I will know that this is something that was replayed and not a fresh copy of the message. If the attacker really wanted to send the message twice, then it would say something like, pay Mallory $10, 5:47. Also, pay Mallory $10, 5:48 p.m. Right? There would be two different messages with two different timestamps. However, if you get two different messages with the same timestamp, you should be pretty suspicious. That probably means that someone is doing a replay attack. Okay. So I think timestamps are the cleanest way to think of it intuitively, but in real life, a lot of people don't use timestamps, and instead they use record numbers. Record numbers are basically the same as timestamps. They're just a unique counter that goes up for every message. So you can either think of it as a timestamp, or you can think of it as this counter that starts going up. And so it could be like message number 500 says pay Mallory $10. And message number 501 is also pay Mallory $10. That would be a case where two different messages were intended, or the same message was intended twice. But if you get message number 500, pay Mallory $10, message number 500, pay Mallory $10, you should be kind of suspicious. That record number didn't change. Maybe someone's doing a replay attack. Okay, so that's how we stop replay attacks within the same connection. At this point, I do want to mention, because it's kind of a common pitfall, if you're still wrapping your head around record numbers, by the way, it's okay if this doesn't make sense the first time around, but the final bullet point here that is worth noting is that the record numbers are not the same as the sequence numbers. They serve completely different purposes, and they live on different layers. What were the TCP sequence numbers for? They were there to help me reassemble the message. So they live at the TCP layer. And the reason why we stamped every message with a number was to be able to reassemble messages. That is not what TLS record numbers are. TLS record numbers are for a completely different thing. And here we're using them to prevent replay attacks. And it turns out that the sequence numbers in TCP, they're not encrypted. When we talked about TCP, did we ever mention cryptography? No. So the sequence numbers are sent unencrypted. However, the record numbers, they have to be sent encrypted. Why do we have to send them encrypted? Because imagine if an attacker tries to replay something, we want to make sure the record number is inside the encryption and MAC protection so that the attacker cannot tamper with the record number, or else that would be bad. Okay. That's the replay attack within a connection. So there are two different replay attacks One of them is between connections. We solved that with random numbers. One of them is within the same connection. We solved that with record numbers. Okay. Whew, finally, that's the TLS handshake. It is the hardest handshake you will see in this class, at least. So I think it takes a couple of run-throughs to digest. I think a useful thing to think about is each of the properties and which steps guarantee each of the properties. Okay, questions about TLS? Open floor. Yeah.
So like the client hello and server hello, like how do we defend against like the attacker, like couldn't the attacker like mess with like the random numbers and always sensing?
Yeah, it's a great question, which is what if someone tampers with the random numbers? And I think these are the kinds of questions, by the way, that you would ask when you're trying to wrap your head around TLS. You know, like ask yourself, or like, you know, talk to your rubber duck or your dog and talk about these questions to try and convince yourself that TLS works. So one question is, what if the attacker messes with the random numbers here? Well, they're going to get caught because remember, there's a step where max get exchanged. And so if they tamper with the random numbers, then one side is going to think, you know, the client's going to think I generated the random number 10, but then the attacker might change it to 20 or something and give the server 20. But when each side generates a MAC, the client's going to generate a MAC on the message 10 because that's what it think it sent. The server is going to generate a MAC on the number 20 because that's what it think it received. And when they compare MACs, they're going to be like, hold on, these don't match. Someone probably messed with my random numbers. That's a good question though. Okay, anything else? Okay, feel free to keep thinking about it. Like, I do think this is one of the denser topics that we end up talking about in the networking unit. Homework will give you some practice with it. So yeah, but it's a fairly complicated handshake, so it's okay. Okay, any other questions? Same question?
Yeah, I'll leave it's the merge related request to the real system and give the guys handshake at the same time, and then stand back at the duplicate and also the
Okay, yeah, this one's a little bit more complicated, so I'll try to give you a quick answer and we can talk about it more later. So the question is, what if the server tries to like relay every single message to the real server? So if this was the attacker and the attacker wanted to, you know, like relay the client hello to the real server, and then when the server hello comes back from the real server, the server like relays it back to the client. The problem is that at this step right here, this certificate has to be the server's real public key. Right? We cannot send the attacker's public key here. It has to be the real server's public key because that's the only one that'll be signed by the certificate authority. So at this point, the client is convinced that the server's public key is the correct one. And so at this point, when you do this exchange, this fake server is not going to be able to decrypt that private key, which means that they're not going to be able to learn what the secret keys are. And so if they don't know the secret keys, they cannot tamper with messages or read the messages. Could they like forward every single message? Sure, but they're not going to be able to change anything about the messages or read the messages. Okay, that's a great point though. Anything else? Yeah, keep them going.
Question about the TLS record numbers.
Sure.
So if a packet gets blocked, does the record number then have to update when it resends the packet?
Yeah, there's a question about what happens if things get dropped. So remember, all of this is happening over TCP. So I don't have to think at all about things getting dropped. TCP will take the encrypted blobs and do the splitting of messages and resending of encrypted blobs for me. So when I send a message with a record number 500, I'm guaranteed it gets there because of TCP. It's a great question though. There was one in the chat about, are the messages encrypted? They are. Here I'm just using this little symbol over here, C sub B or whatever, to note that they're encrypted, but that's also a good point. But they are encrypted, they are MAC'd. Okay. Final thing I'll mention, because I guess no one asked it. Every semester, like sometimes people call me out on this, sometimes they don't. So I guess not this semester, it's okay. Okay, sometimes people ask me, tell me about the 4 keys. So I'll tell you. So technically, if you really wanted to, 2 keys is probably okay. 1 key for encrypting everything, 1 key for macking everything. The main reason why you might want 4 is so that the messages in one direction get encrypted with 1 key, and the messages in the other direction get encrypted with another key. Technically, it's not necessary. Maybe there are some like really obscure attacks that I don't know about, but at least for what we're presenting here, the 2 key approach would have worked okay. The 4 key approach is just us being more paranoid. And so messages in one direction get encrypted with 1 key, messages in the other direction get encrypted with a different key, but both sides know both keys, right? That's the key. Okay, that is the key, no pun intended. Both sides know all 4 keys. And so even though the messages get encrypted with different keys in either direction, both sides are able to encrypt and decrypt them. Okay, and same thing with the MACs. There's 1 for macking in one direction, 1 for macking in the other direction. you can imagine that these solve something like a reflection attack, which we're not going to talk about in this class, where someone copies down all the ones and zeros in this direction and then tries to send it back in the other direction. The fact that we're using different keys might also help stop that, but it's a little bit out of scope. I just wanted to bring it up in case people are curious. Okay. Someone asked if RB and RS are similar to the IV. I think you could probably say that they're similar to IV in that they're public and they're there to make sure that the encryptions and the secret keys come out different every time. They're not exactly the same, but I think there's a reasonable comparison. Okay. Those are all great questions. Anything else you want to grill me on about TLS before I tell you about some properties of this thing? Okay. Properties. So forward secrecy. This one we've seen kind of, sort of. So today I'm going to like make it very explicit. So remember, the idea of forward secrecy is that if an attacker hypothetically wrote down everything they saw now, maybe at the present time, they have no idea what it says. And to them, it's just a bunch of ones and zeros. They don't know what it says. But imagine if they recorded everything now, and then sometime in the future, they hacked into your computer and learned all of your secrets, or somehow you exposed all of your secrets, or they got leaked. Well, forward secrecy asks the question, if we have the scenario, the attacker writes stuff down now, and the secrets get leaked later, are you protected against the attacker in the future reading the messages or looking at the messages that they wrote down from the past and decrypting them? If the answer is yes, you're protected against that, then forward secrecy is guaranteed. And if you are not protected against that, in other words, an attacker in the future could get the values that they wrote down and decrypt them using the secrets that they've learned, then forward secrecy is not guaranteed. Okay, so that's the property of forward secrecy. And so this is what's going to help us distinguish which of the two approaches is better when it comes to exchanging pre-master secrets. So in RSA-based TLS, there is no forward secrecy. And let's think about why. So the reason why there's no forward secrecy is because what can the attacker write down? The attacker can write down the random numbers. Those are sent publicly. The attacker knows those. And the attacker can write down that encrypted pre-master secret. Remember in the RSA version, we send the pre-master secret, encrypt it with the public key of the server, and that gets sent over the channel. And so the attacker can see that. And if later the adversary comes back or the attacker finds out what the server's private key is, it gets leaked, the attacker learns it, well, now they can take this encrypted value and they can decrypt it because they know the private key, it's been stolen. And once they know the decrypted pre-master secret, and they know the random numbers, they can derive the symmetric keys and they can decrypt all the stuff that they previously wrote down. And because this attack is possible, the security property of forward secrecy is not guaranteed for RSA TLS. The main problem here is that the private key is kind of a long-term thing. It's usually kept around for a long time. So if you encrypt something with the public key and expect someone else to use their long-standing private key to decrypt it, then if the private key gets compromised, then you might have bad news. Okay, by contrast, Diffie-Hellman does guarantee forward secrecy. And the reason why it does is because the Diffie-Hellman handshake does not rely on long-term secrets like the private key that I'm keeping around. Because what will Diffie-Hellman do? Well, first think about the messages that get sent back and forth. The two messages that get sent back and forth are Diffie-Hellman favorites, G to the A mod B, G to the B mod P. And so you can imagine if the attacker writes down these two values, at the present time, they don't know what the secret key is, G to the AB. And also remember in Diffie-Hellman that A and B get destroyed as soon as they both share a key because A and B are not the actual key. The actual key, the secret, is G to the AB. That's what everyone cares about. So as soon as I derive G to the AB, I can throw A and B away, destroy them, never to be used again. So even in the future, if an attacker comes back and compromises all of my secrets, they're not going to know what A was, they're not going to know what B was, and with just these two values, they have no hope of coming up with G to the AB. Okay, so that's why Diffie-Hellman provides forward secrecy. It's because of the fact that the A and the B, the secrets that get used, are thrown away right afterwards, whereas in RSA TLS, we're relying on a source of secrecy, the private key, that gets kept around for a long time. Okay. So forward secrecy is the reason why we prefer the Diffie-Hellman version over the RSA version. And so in older versions of TLS, you had a choice. When both sides said hello, they could choose which of these two to use. But nowadays, in the most modern versions of TLS, there are a couple of fixes that we've made. So you don't have to know all of these in too much detail, but there are a couple of fixes that hopefully feel good for users of the internet. So one of them is nowadays RSA is no longer supported. You cannot use RSA anymore. You are forced to use the Diffie-Hellman version because it's more secure. So the designer said that other version, it wasn't so good. You can no longer choose it. It's no longer in the list of cryptographic protocols that you can choose. You have to use Diffie-Hellman. And secondly, there's a little bit of a performance optimization. This one is very similar to the WPA performance optimization. Do you remember in the WPA handshake, it was like 6-way handshake and 6 was too many, so we crunched it down to 4. Well, it turns out that if you're guaranteed to be using Diffie-Hellman ahead of time, you can actually take that long handshake and compress it just a little bit by sending G to the B and G to the A in the client hello and server hello steps. So you save yourself a step there. I don't have a picture of it, but the idea is very similar to the WPA version. I take that really long handshake and I try to send some of the messages at once instead of across different steps to save the amount of round trips that I have to make back and forth. Okay. And the final thing that was added in this latest version of TLS is, well, older versions of TLS, they use like MAC that encrypt and MAC, and you have to think about which one was more secure. Nowadays, modern TLS chooses one of those fancy modes that gives us both integrity and authenticity at the same time. We briefly saw those in the cryptography unit. TLS now uses those. So you get one key or one encryption algorithm that also provides integrity. And that's what we use to secure our messages. So we don't go and use like MAC that encrypt because that wasn't secure. And it turns out that the use of MAC that encrypt on older versions of TLS, it actually did cause problems. And I think there was a slide on that back in the cryptography unit, but you don't have to know that. Okay. So there are some updates. You just have to know the highlights. Basically, there are performance optimizations and also security optimizations or security improvements, that is, based on things that we've learned in the past. Okay. So end of like how TLS actually works. So now it's time to talk about TLS in practice. So any final questions on like how the protocol actually works before we talk about this? Okay. By the way, I didn't draw this, but like, how cool is that, right? Wow. Okay. If you would like to contribute, we have some empty slides. So, shoot us an email. You could be the next person with something on here. Okay. Very cool. So shout out to them. Okay. So let's think about some things that you might care about when you're using TLS in real life. So one of them is how efficient is it? So in TLS, what are the things that might take time? Well, one thing that might take time is public key cryptography. Remember this? Like public key cryptography uses all this magic modular math and it's so slow. So technically, public key cryptography will introduce a little bit of performance overhead. In general, it's not something you'll really notice, but it does affect you when you're first creating the handshake. Because when you first do the TLS handshake to start up the connection, you have to do that Diffie-Hellman key exchange. And that could take a little bit of time, depending on your particular hardware or implementation. It could take a little bit of time. So technically, if we really want to be honest and think about the costs, public key cryptography, it counts. Okay, what about symmetric key cryptography? Because now, compared to regular old TCP, I have to actually encrypt every single message that I send. Is that expensive? Should I count that against the performance of TLS? I would argue no, because symmetric key cryptography is cheap. It is just shuffling all the bits around. We know that's fast. In fact, modern computers, they know that everyone runs AES. You run AES, I run AES all day, every day because of stuff like TLS. It's just such a common protocol. And so modern computers, like the people who wire up the circuits, they actually specifically wire up the circuits in some way that's like beyond my understanding to make it so that AES runs quickly. So not only are our computers really good at computing symmetric key cryptography, they are like specially built to be really good at AES, right? It's like an AES computing machine. It's really good at it. And so I would argue, at least personally, that the symmetric key cryptography should not count against the costs. Technically, is it slower than TCP? Yeah, kind of, because you have to encrypt things. Are you ever going to notice the benefit? In my opinion, no. So I guess it depends on your particular setting, but I would say for like most modern settings, you're never going to notice this. So basically free. Okay, so I don't think that counts against efficiency, but maybe you disagree. Okay, the final one that I do think counts is latency. So latency, remember from any prereq, is the amount of time it takes for a message to show up on the other side. And so here, there's a little bit of extra waiting time because when you first connect to the server, like think about what you have to do in plain TCP. Three-way handshake, SYN, ACK, ready to start sending messages. What about in TLS? In TLS, you have to do SYN, ACK to get the TCP connection running. And then you have to do this gigantic handshake with like 6 different steps with a bunch of public key cryptography. And only after all of that stuff can the first message be sent. So the first message will have a little bit more waiting time, but after that first message and the handshake is done, you shouldn't really notice any performance drawbacks. So in my opinion, the trade-off here is that there's going to be a little extra waiting time before the first message, but I would say in most cases it's worth it because now all your stuff is secured, but it's up to you, I guess. If you really care about that first message showing up instantly, maybe something like UDP is better for you, but your call. Okay, great. So that's how we think about the efficiency of TLS. So here's a really cool property of TLS. So remember how we said there were all these different attacks. Remember like ARP spoofing, the attacker could become a man in the middle, and we just kind of said, okay, deal with it. And like DHCP, the attacker could become a man in the middle. Okay, deal with it. BGP, the attacker could become a man in the middle. Deal with it. So finally, TLS, this is what's going to allow us to deal with all of those attackers by giving us this really beautiful property called end-to-end security. And so what end-to-end security says is that for TLS to work, you need 2 things to be true. The client has to be secure. No one can attack my computer and hack into it. The server has to be secure. No one can hack into the server and steal their secrets. If these 2 things are true, literally every single person in between me and the server, or the client and the server, could be malicious. There could be 20 man in the middles standing between me and the server, ready to tamper with things. There could be 50 of them, doesn't matter. Everybody in between could be malicious, and TLS is still going to stop all of them. And the reason why is because remember, everything is secured with cryptography, everything has confidentiality, everything has integrity. So even if there are like tons of people in the middle who've like hijacked ARP and DHCP and whatever, it's still okay because between me and the server, everyone can be insecure or an attacker, and they're still not going to have any ability to read my messages, tamper with my messages, or impersonate the server. Okay, so it's a really great property because it allows us to take all of these different networking attacks that possibly result in man-in-the-middle attackers and just say all of them are defeated in one step or with a single protocol. That's pretty cool. Okay. So it's a great property, but like don't get too excited over it and say, okay, this solves all of my problems, because remember how we said end-to-end security guarantees things as long as your computer is good and the server is good. But what if the server is not good? And so end-to-end security does not stop one of the endpoints itself being malicious. So for example, imagine if you made a TCP connection, or sorry, a TLS connection to like the attacker's website. Okay, great. It's beautiful. It's end-to-end secure. Everyone in between you and the attacker cannot stop you, but the attacker can still mess with your connection, right? Or give you bad data. So if you make a beautiful end-to-end secure connection using TLS with the attacker, you're still vulnerable because who are you talking to? Using this beautiful secure connection, you're talking to the attacker. And so end-to-end security helps stop people in between, but it does not stop the end user being an attacker. So you still have to be careful. This is not a magic wand that stops everything, but it does stop all of those network attackers in between that we've seen. Okay. Question?
Does this certificate like confirm the identity of the server?
Yeah, there's a great question, which is, doesn't the certificate confirm the identity of the server? But what if you were intentionally somehow connecting to the attacker's website? And so you get the certificate and the certificate says, yes, this is really the attacker's website. And you're like, okay. And then you connect to the attacker, things will still be bad. So that could happen, for example, in the web attacks where we like trick someone into making a connection. So it's a great question though. So here it does stop people pretending to be someone they're not. But if you are really talking to an attacker and you're really intending to talk to them, then you get an end-to-end secure connection, but it's with an attacker. So you can't say end-to-end security solves all of your problems. Okay, it's a good point though. Okay, TLS is wonderful, has all these wonderful end-to-end properties, but again, we have to be a little bit careful. We can't go out and celebrate yet because there are a couple things it doesn't provide. So here's a property that we're going to see again at the very end of class, which is anonymity, and TLS does not provide it. So this is a property that you might want, maybe you don't, but the property is that you do not, maybe you don't want other people to know who you are. So you don't want other attackers to know who you are and who you're talking to. And TLS is not going to do that for you. So TLS does not promise to hide who you are. An attacker could still figure out who you're talking to and who you are. And so examples of how they can do that, well, they see the certificate. The certificate is in the handshake, it's unencrypted, and it says the server's public key is this. So an attacker could possibly read that certificate message and say, oh, okay, this is the server they're talking to. So an attacker could figure out who they're talking to. You can also imagine that all of this is built on top of TCP and IP, right? So when I create these beautiful encrypted messages, I still have to take them, split them into packets, and send them using the IP protocol. And what does the IP protocol include? It includes that header with the source IP and the destination IP. That's not encrypted. That's something that I'm building on top of. And so the IP header is still unencrypted. So someone could also use that to figure out who I am and who I'm talking to. So all of this is to say TLS does not provide anonymity. Attackers know who you are. Okay. Here's something else it doesn't provide, which is it doesn't provide availability. This is another property that we'll see in more detail later, but for now, you can imagine availability is the guarantee that your messages will get there even if an attacker is present. And this is not guaranteed with TLS. And so why is that true? The easiest example is a man in the middle can just take every single packet that comes over and it's encrypted. It's got max. How can the attacker tamper with it? Well, they can't, but they could delete it. And so the attacker could see every packet coming over. They can't tamper with it or change what it says or read it, but they could just be like, delete, 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 and then no messages ever show up. And so that would ruin the availability of your TLS connection. So if someone really doesn't like what you're doing, maybe they cannot read what you're saying or tamper with what you're saying, but the man in the middle could potentially just delete every single message. Okay, here's a more exotic attack, which is, remember that TLS is built over TCP. And so this one is kind of funky to wrap your head around. I would say if you get this though, like you have a rock solid understanding of networking and the like layered idea in the networking protocol. So if you trust the layers of abstraction, you'll remember that in TLS, I could have this encrypted message, right? It's encrypted, it's got a MAC, it's beautiful. Okay, there it is. And so how do I send this thing? The way that I send it is using TCP, right? So the way that I'm going to send this message is I'm going to wrap it in a TCP header and then send it. Okay, there it is, TCP header. And then this is the packet that I send over. So I have this beautiful encrypted message that nobody can ever touch or tamper with. I wrap it in the TCP header and I send it over. But this TCP header, it is not part of the encrypted message. And so this TCP header is still vulnerable. I'm sending all of these encrypted ones and zeros over a TCP connection. And because I'm sending it over a TCP connection, that reset injection attack from last time, it still applies. Because how do you do the reset injection attack? You inject something with the right sequence numbers and a reset flag set. Can someone do that here? They can, because the reset flag is not part of the encrypted message. So someone could, in the header, inject or add the reset flag, and they can stop the connection as well. Okay. It's kind of tricky, but turns out to work here. And the reason why it works is because TLS is built on top of TCP. Okay, questions? Yeah.
So would TLS work if you, let's say, didn't care about packets actually getting there reliably, and then you just did it over the data?
Question was, will TLS work if you don't care about reliability? That's an interesting question. I mean, TLS is built on top of TCP, so like it already assumes the reliability. If you wanted a version of this that doesn't guarantee reliability, you probably could build one. It would just look different. So I don't know. It's an interesting question though. Okay, but since we're building it on top of TCP, we get the reliability guarantees and the ordered guarantees of TCP. The flip side is that we're also vulnerable to TCP attacks like reset injection. Okay, yeah, good question though. Okay, that's one other thing that it does not provide. And so finally though, we have actually reached the point at which our networking stack, as we go from the bottom and come up, has actually touched the web stack, which started at the top and moved down. And they've met in the middle. Right? So it's like beautiful moment where they both meet. And so this is the point. I heard 61C whispers. Has everyone taken 61C with like Dan Garcia? Because in 61C, they also have this moment where like you start layering up and then like start layering down. And then when they meet, everyone like starts like getting up and walking around. Okay. Has anyone like experienced that? I experienced it many years ago. Okay, so he still does it now, I guess. Okay. Okay, so we're not gonna do that. You can go and like walk around in circles outside later if you would like to. I'm not going to. But it's still a moment we're celebrating, right? Which is that, well, we've started at the bottom and built up progressively more richer layers. And we finally gotten to the point where we've met the application layer. And so now, because we have TLS, we can now build anything we want over TLS. TLS provides a way to send messages from one computer to another with cryptography guarantee. What can I do with that? I can build the web. I can build HTTP using this tool that allows me to connect one computer to another. Because remember when we talked about web, we kept saying, well, there's a way for one computer to send a message to another. That's going to be the networking unit. You've built all of that from the bottom all the way up. You've built it. And now you can build the web on top of it, which is really cool. So now you finally understand why HTTPS and HTTP exist. Both of them are pretty similar protocols at the web level. The only difference is that if you use HTTPS, you are sending messages over a TLS connection. If you use HTTP, you're sending messages over a plain TCP connection, no extra TLS added on top. That's why those two protocols exist. Now you know. Okay, and so HTTP is one of the things that you can build on top of TLS because HTTP requires a way to send messages between two computers. You have it as TLS, and now you can build HTTP on top and then build all those web applications. But there are also other things you can build. So for example, you can build like SSH as a way to like remotely connect to a computer. You can build file transfer protocols. All sorts of interesting application things exist built on TCP and TLS. These are the building blocks that allow me to make all these applications work. Okay, final note is that all these applications live above TLS. And so all the attacks at the web unit, like SQL injection, XSS, CSRF, these do not, or TLS doesn't defend against this. And it kind of feels maybe reasonable because if I have a computer and I make this beautiful end-to-end secure connection with another computer, but the other computer sends me like malicious JavaScript, well, I'm still in trouble, right? So even though the man in the middle's network attackers cannot mess with that connection, if someone is sending me bad JavaScript, I'm still going to run it, and so I'd still be in trouble. Or if my computer makes a connection, beautiful end-to-end encrypted to another server, and then I send a SQL injection payload, well, okay, no one can tamper with the payload, but the attacker or the server is still going to get attacked by it. Okay, so we don't stop the vulnerabilities at the very top layer. We only stop the networking attackers at this layer and lower layers as well. Okay. There were a couple blue slides here. You don't have to know these. This one's kind of interesting, so I'm not going to talk through it in too much detail. But the interesting thing is basically that modern computers try to default to HTTPS, but you can try and force them to downgrade to HTTP. It's kind of cool. It's there if you would like it. Okay, well, I guess these are blue. Okay, so actually, I think what happened is I made them optional because I ran out of time last semester, but this time I have not ran out of time. So unfortunately, you have to know some of these things. So I'm going to make them unoptional, but I promise you they're not too bad. So okay, let's do it. Okay. Okay, so you don't need to know SSL stripping. I'm okay with that. I probably should have checked these before I came here. Oh, well. Okay, so unfortunately, you have to know these, but I promise you they are pretty straightforward. Okay, so, and I think it's kind of interesting too. It's like a human design problem. So originally, back in the day, the way that you would communicate, or the way that your browser would tell you whether or not you're using HTTPS or HTTP is they would do this. If your connection is HTTP, no lock symbol for you. It's not secure. If it's using HTTPS, you get the lock symbol. Okay, straightforward enough. But the problem here is that like we're not punishing people enough for not putting or for not implementing HTTPS, and we would like to incentivize everyone to use HTTPS. So here it's kind of like we're giving you a little reward if you use HTTPS, and if you don't use HTTPS, you don't get the reward, but things still look okay. And so this encouraged people to start adopting HTTPS. But nowadays, like we want everyone to adopt HTTPS, right, and TLS, because it's just the more secure thing to do. And so nowadays, when TLS is so widespread and we want everyone to be able to use it, we've swapped up the rules a little bit. So nowadays, browsers do this instead. So nowadays, if you go onto the website that does not have HTTPS, right? You just use regular TCP. Not only do you not get the lock icon, you get punished with this like not secure icon. And so this is a way to try and encourage everyone to adopt HTTPS by explicitly showing you that this is not a secure connection. Okay, so it's a little bit of human engineering. I find it interesting that browsers can change their user interface like this to encourage the world to adopt HTTPS, which you should. Okay. I guess the final thing I will note, though, is that the log icon, while it encourages people to adopt HTTPS and TLS, you do have to be a little bit careful because it does not guarantee that things are secure, right? You shouldn't see a log icon and immediately think, oh, everything is wonderful, right? Because the attacker can add their own log icon. The log icon could mean you have a secure connection, but you're talking to the attacker. So you have to be really careful. The log icon is good, but it is not foolproof, right? So we still have to think about our users. This is a nice way to kind of try and convince the websites and the servers to try and adopt HTTPS and support TLS connections and upgrade their softwares so that they support TLS. But we still have to be careful with the end users. We don't want to like give them false hope in the lock icon, because if I make an HTTPS connection to like attacker.com, the lock icon is going to show, but I'm talking to an attacker and who knows what they're going to send to me. Okay. This one is not in scope, so okay, I guess I'll change it again. But I'll take this one out of scope for you. So you don't have to know the details of this one. It's basically another PRNG sabotage one. This thing just comes up over and over again. We have so many examples, but it basically says, if you use a bad PRNG, you're kind of in bad shape. Okay. I guess I'll be nice to you. I don't want to go through the trouble of putting these back in scope, so I won't test you on these. But I find this part really interesting, so I'll still talk about it. So the reason why I find this part really interesting, and it does have some takeaways that I think are valuable, is this is kind of one of those places where the networking protocols, like the ones and zeros and how we actually implement things, actually has to meet the real world, where we have to think about what entities and organizations do we trust. So as we've already seen, right, like ones and zeros in a computer, we can build trust and we can build, certificates and these schemes that provide integrity. But ultimately, trust also has to come from real life relationships. So I find that really cool. Okay, so you've already seen this. This part, I guess you probably should know, which is that in TLS, the server sends the certificate. And I told you the certificate is verified by someone that you trust. But who is that someone that you trust? That's what we have to figure out. Because all of TLS security relies on that certificate telling me what the server's public key is. So I have to know who actually signed that public key and why do I trust them, right? Like that's not something that a computer or an algorithm can answer for me. That is something that I have to answer using my real life trust, which I find really interesting. Okay, so this is just a review of why certificates are in there. And so one thing that happens sometimes is that when you receive the certificate, you don't know who signed it. And so that's a problem because all of TLS relied on the fact that that certificate that got sent was signed by someone that you trust. What if you don't know who signed it, or the person who signed it is not someone that you trust? Well, browsers try to tell you this and warn you about it. And we talked about this all the way back in lecture 1, 2. Like, yes, technically you will see this and it's trying to warn you. Like, what is it actually trying to warn you about? Now you know, right? It's trying to warn you about the fact that the certificate that got sent is not a certificate signed by someone that you recognize. And it's asking you, do you want to place your blind faith in this certificate that you've never seen before? Or would you like to be cautious because maybe that certificate signed by someone that you don't know, maybe an attacker signed it. Maybe it's not the real public key of Google.com. Maybe it's an attacker who made their own fake certificate and signed it. You don't know. And so now it is up to the user to put their trust in this certificate that they've never seen before. So that is what a browser is trying to tell you when it shows you this. In real life, what do most users do? Like accept, right? They just want to get it over with. They don't know anything about the certificate stuff, but now you do. So that's what happens. You can consider human factors. But if you're curious, that is what a browser is trying to warn you about when it tells you about this unknown certificate authority problem. It doesn't know who signed the key, and that could be scary. Okay, and we know it's scary because if you don't know what the server's public key is, then you could be talking with someone impersonating the server. That could be bad. Okay, that's the unknown certificate authority. So now you know. If you want to know how to verify certificates, I don't know why you would do this unless you're like very bored. but I was very bored one day, so I did this. So if you're really curious, on Firefox, I don't know if this is still true because Firefox is newer these days, but, or like it's been updated since I did this. But if you go on the website, you can click through more information, security, view certificate. There's the certificate right there. So if you've ever been curious, you can view it. I don't know why you'd ever be curious, but if you are, there it is. You can even see things like, oh, it's signed using RSA. There's the signature. It's kind of cool. Okay. Other problems are, what if this server's private key gets compromised? What if someone steals the server's private key? We have to deal with revoking certificates. We've talked about that before in the certificates lecture. Okay, this is the part that I find interesting, which is how do you actually know who signed these keys and how do you trust them? And the way that you trust them is that your browser actually has the public keys of like 100-ish root certificate authorities baked into your web browser. So when you download Firefox or Chrome and you don't update any of the default settings, you are implicitly, without anyone asking you for your consent, putting your trust in these 100 organizations who have the power to sign TLS certificates. That's what you're saying when you accept or when you download Firefox or Chrome. So somehow you're putting your trust in maybe like the Mozilla organization or in Google, that they have actually properly vetted these organizations. And somehow you're also implicitly putting your trust into these organizations. Should you trust them? I don't know. It depends on how you feel. So these organizations could be anything like companies, like VeriSign is a company that issues certificates. There are nonprofit organizations. I'd imagine there are like government organizations in here. How many of those do you trust? That's a question for you. It's kind of interesting. And so some of these actually might not be trustworthy. For example, if they get hacked, then you can't trust them anymore. Or if they can be bribed, the companies can be bribed, well, then now you can't trust them either. And it turns out that this has happened before. So some certificate authorities have been hacked by people. Some of them have been hacked by people. Some of them have been hacked by people. There's a lot of these. And so sometimes when you get hacked or when someone bribes you and you accept the bribes, the web browsers will have to delete you from the list of trustworthy authorities. So these companies will like just get nuked from the list of trustworthy certificate authorities. But all of this happens in real life. It's not a security algorithm that we try and figure out to like cryptographically know that these people are untrustworthy. The only way that we know is because of their like shady business practices in real life, or the fact that they just get hacked a lot. So yeah, that's interesting. Okay. But the takeaway basically here is that coming up with these trust anchors is hard, and it relies on real world trust. You cannot rely on just the ones and the zeros and the algorithms to give you trust. You need to put your trust into organizations, Google, Mozilla, VeriSign. So that's kind of interesting. Okay, there are ways to solve this, and we're not going to talk about them in this class. We've done optional lectures on these before, so if you're curious, they're there, but I'm not going to talk about them for time. Okay, there are lots of these apparently. Okay, the final thing I do want to talk about, because I find it interesting, is modern certificate authorities. There are a lot of them. And if you've ever wondered who is the largest certificate authority, it's called Let's Encrypt. This is real stuff that you can go out and implement. So Let's Encrypt is the world's largest certificate authority. And the reason why they are the world's largest authority is because they are free. So when you ask for a certificate, they give it to you for free. You don't have to pay. I believe they are organized by a bunch of nonprofits that care about internet security, and they realize that charging money for certificates causes people to forego security, or they have to make a trade-off of like money versus security. So they decided, to heck with all that, I'm going to issue certificates for free. The nonprofits will pay for it somehow. And so because they're free, well, the reason why I'm telling you this is because you have no reason not to implement TLS on your web servers if you ever build one. Because I'm telling you, it's free, right? So do it, okay? And Let's Encrypt also tries its best to make everything as easy as possible. There's lots of different ways in which they try to encourage people to use their service and to generate certificates and to use TLS and implement TLS. And so, for example, one of the ways that they try and make sure that things are easy, this is the way that they issue a certificate. In like modern software, there are like tools that can even automate this stuff for you. So it's pretty cool. But if you're ever wondering how the certificate authority knows it's you, this is how they do it. So you can read that if you're interested, but seeing as I'm short on time, I'll leave it to you. But the takeaway here, Let's Encrypt is free. There is no reason not to implement TLS in 2023. Okay, to summarize, here's the handshake. I think it's a lot of different steps. It's pretty dense. And so the way that I think about it is try and think about all of the different properties that I care about, confidentiality and integrity I care about, the two types of replay attacks in the same connection and different connections, I care about those, making sure I'm not talking to an impersonated attacker, I care about those as well. And these are the steps that guarantee them. So I encourage you to like play around with the handshake, think about which steps guarantee which, and the homework will also give you a chance to play with those. Talked about the properties, so forward secrecy we care about, and that's why Diffie-Hellman is superior. Why RSA is no longer allowed. We talked about the end-to-end security property. It stops a bunch of networking attacks that create man-in-the-middle attackers. They are all now stopped, but you have to be careful because end-to-end security does not stop you if the end host itself is malicious. We also talked about two things that are not provided by TLS, anonymity and availability, and we talked about how it links up to the application layer. And finally, I gave you a quick rundown of why trust and certificate authorities can be hard, relies on real life trust. Okay, end of TLS. So come back next time. There's a couple more networking things I got to show you, and then we'll be done for the semester. Okay, see you. And good luck on project 2.